Welcome back to the final video for elimination and inverse matrices. And this video is the one that's going to kind of bring everything together for what we've been doing this entire, really this unit, and trying to solve the equation AX is equal to B. And focusing on this A and thinking about how we can break it down into different factorizations. And in Unit 3, we'll start getting what the full picture of this kind of looks like. But focusing on the A, we've been talking about how by using elimination matrices, I can multiply by these EIJs with A and transform my matrix from A to B into something that's upper triangular. And what we ended up finding out is that if this all multiplies into a single elimination matrix, we'll just kind of call it one big E to get into U. If I take the inverse of this, we have a really interesting factorization for A in terms of its breakdown, but we didn't really know necessarily how to find this inverse or really what an inverse to a matrix was. And so in the previous lesson, in the middle of this section, the second video set, we discussed like how you find the inverse when a matrix is invertible, what happens when you have an elimination matrix in particular, and talk about its inverse. And we're going to get into that today. And one of the first things we need to talk about, though, is because we're multiplying a bunch of elimination matrices together, what happens when I want to ultimately inverse all of these? What does that look like? And so one of the first facts that we'll talk about is that if I have two matrices being multiplied together, AB, if A and B are invertible, so if A and B are invertible, square matrices, then if I want to find the inverse of AB, this inverse is B inverse, A inverse. In other words, the idea is that when I inverse a product of matrices, the product happens in the reverse order. And that kind of makes a lot of sense when you think about if I have this multiplication occurring and I want to undo this multiplication so that I get I, right? The idea is how do I undo this to get back to the identity matrix? I'm multiplying on the left side of this matrix, so the first thing that I need to multiply by is A inverse. And so if I multiply by A inverse here, then these two things would become the identity matrix, but then I need to get rid of B, which means I need to multiply on the left by B inverse. So in terms of the original problem, if I have AB, what do I need to multiply with that will cancel it? Well, that's overall AB inverse or B inverse A inverse, this idea that it needs to swap. And so he gives a proof in the text, which it's pretty easy to read, so I'm going to kind of leave that. And then there's an extension for you to read. There's an extension in there on the next page, essentially page 52, equation 8, that starts to build on this concept of if I have more than just two matrices being multiplied together. So say, for example, we have ABC, and I want to find the inverse of this product. The inverse works in the opposite order from left to right. It would be C inverse, B inverse, A inverse. And this concept is really important because, again, in the overarching theme, we're taking a matrix and through the process of multiplying by a bunch of elimination matrices, taking it down to U. Well, I have multiple matrices being multiplied together. So if I want to do the inverse of that, slowly peeling those off, multiplying in the reverse order for the inverse, that process looks like this. This is how it's essentially defined. Again, you can imagine if I'm multiplying a bunch of matrices A, B, and C times another one, if I'm trying to undo that multiplication to move it to the other side, it looks like this. It works in the exact opposite order. And so applying this to elimination matrices now is really kind of what I want to focus on in terms of this video, because ultimately I've got an example, and it's an example from a previous video, 2.1 actually, that we changed to be upper triangular and kind of show you this process. And the process then really leads itself into the next section, 2.3, when we're actually going through and doing this special type of factorization. So for example, and this line again is taken from the text, let's say that we are going through the process of elimination and we're taking the elimination matrix E, and what that matrix is going to do is it's going to subtract 5 times row 1 from row 2. And so if we do that to a matrix, then my elimination matrix E would look something like 1, 0, 0, negative 5, 1, 0, and then 0, 0, 1. So if I multiply this matrix on the left-hand side by 2A, for example, then this is essentially going to take row 1 and multiply by negative 5 and add that to row 2, so aka creating that subtraction. And remember, when we really kind of initially defined this when I was sick in the 2.1 video, is we defined this as Lij, where we want to treat this, because of the subtraction, as if it was a negative. Right? That's how we kind of wanted to view it. So my essentially working with row 2, column 1, trying to eliminate, say, this entry by doing this subtraction, the input here for the elimination matrix would be ultimately negative 5, because it's that negative entry, the negative Lij. Now, what's fascinating, though, is if this is what E is going to do, and our focus is around E inverse, what's really beautiful about this is that the inverse is going to literally do the inverse operation of what's happening. So instead of subtracting 5, E inverse is going to add 5 times row 1 to row 2. So the inverse matrix, according to this kind of logic, is that the matrix should be 1, 0, 0, 5, 1, 0, 0, 0, 1. That this will be the inverse operation to what this elimination matrix is doing. And we can check that these two things are inverses by multiplying them together. And I'm going to essentially do the inverse on the right-hand side. If I multiply these two matrices together, just going row by column, notice how 1, 0, 0, 1, 5, 0 would give me 1. And then 0, 0, the rest are zeros, so 0, 0. The second row, and this is where it gets kind of interesting, I would have negative 5 times 1, but then 1 times 5, and because they're the opposite signs but the same multiplication, with this diagonal being 1, so those are going to eliminate each other out, and so we'll get a 0 in this entry. And then we can kind of see as I'm doing this multiplication, because it's 0, 1, 0, the only entry that gets recorded here is whatever the middle entry is. So this becomes, again, 1, and then this ends up being all zeros. And so you can kind of start to see how the identity matrix is coming out of this, and it turns out, again, that the third row itself is the identity matrix. And so by definition, from what we've been talking about, this tells us then that this process of thinking is correct, that if I want to find the inverse of an elimination matrix, whatever that I'm initially subtracting, that value is what actually gets put into the entry for my elimination. So one of the, not confusing things right now, but just one of the notation things to keep in mind is that when I refer to this Lij, these are actually the entries by row and column for the I and J there for the inverse of my elimination matrix. And not just necessarily for each individual elimination matrix, but the overall elimination matrix that we're going to ultimately try to find when I'm looking for that one matrix kind of answer. Now, he goes through and he shows off another scenario, so I think it's going to be interesting to showcase this because it kind of gives some numbers. And again, I want these videos to kind of show more examples, so I'm going to try and do that as the math gets a little bit more complex. Let's say now that we have a new matrix F, again an elimination matrix specifically. And what F is going to do is it's going to subtract 4 times, this time row 2, from row 3. So this is essentially acting like getting rid of that 3, 2 entry. So like it's almost like we've already zeroed out everything underneath my first pivot, and now we're working in that second column, trying to zero out that entry in a 3 by 3 underneath that second pivot point. That's kind of what's happening here. Well, if that's the case, according to our kind of theory right now, if I wanted to find the inverse of this elimination matrix, then what that's going to do is add 4 times row 2 from, all right, actually I'll just say 4 times row 2 to row 3. and row 3, essentially adding those two things together. So I have my initial elimination matrix as being 1, 0, 0, 0, 1, 0, 0, negative 4, 1. And then according to this, my inverse for this elimination matrix just takes away the negative. So 1, 0, 0, 0, 1, 0, 0, 4, 1. And how we read it off. Works very similarly. Now, notes, I kind of show the multiplication again. I'm not going to go through and show it, so you can kind of trust if you're to do the multiplication. By multiplying these rows with these columns, this is going to replicate the first two rows of the identity matrix. What we really need to test is what happens when I multiply this row times each column, and you can quickly see 0, 0, which is really important, and then the last one giving me 1. So that these indeed are inverse matrices from one another. Now, the interesting factor that kind of occurs here is if we were to now take that elimination matrix E and take that elimination matrix F, and what if we ended up multiplying those two things together? Because what we're ultimately doing with this example was focusing on two elimination steps. But we know that if I have a matrix for A, if we're applying E and then I'm applying F, these are going to interact with one another. F is going to affect whatever E did to A, right? Because E is doing something to A. And so let's say, for example, I have E, again, was 1, 0, 0, negative 5, 1, 0, 0, 0, 1. Let's go through and do the multiplication here. Let's do F times E in terms of our setup. And let me make sure I have the order. Yeah, okay. So if we were to do F times E, I'm going to write these side by side. So F, E. If I multiply these, so I'm going to have my row 1 times column 1, so that's 1, 0, 0. We follow through. Again, notice how this is keeping row 1 the same. This is ultimately going to keep row 2 the same, so 0, 1, 0, so 0, 1, 0, 0, 1, 0, 0, 1, 0. So negative 5, 1, 0. This entry is going to affect the third row by multiplying row 2 by 4 and subtracting that with row 3. Well, that's going to alter my very first entry because see how this negative 4 and the negative 5 will align when I'm doing my multiplication. I'll get 0 times 1, which is 0, but this is ultimately going to give me a plus 20 times 0. So this actually gives me an entry here in my row 3, column 1. And then when I do the remaining pieces, it lines up with what we initially were doing. This is going to be negative 4 and negative 1. We see those still individual pieces, what we're trying to do with the elimination. But what's interesting is that this 20 comes from the combination of these two elimination steps when we're trying to eliminate those two pieces. So when we're looking at this from this kind of viewpoint, they interact with each other so that we get some random, and not necessarily random, but numbers that don't really connect with what we're doing in terms of my eliminations. We may not necessarily be multiplying my row 1 by 20 and then subtracting row 4 with row 3 in terms of thinking through our elimination processes. And so there's not a lot of great things we can get from this. And that's where the inverse idea comes in. Because if I want to find the inverse of this, like remember that we're essentially saying if I have AX is equal to B, if I bring these to the other side to solve for X, that would involve dealing with inverses. And even better yet, we're really kind of saying that this is equal to U. I can bring this over here to solve for A and get A by itself. If I want to find the inverse of this, because they're lower triangular, their inverses exist. I've got one in each pivot. So they're square matrices, so that means this inverse is equal to this. E inverse, F inverse. Now, E inverse we had earlier. That was 1, 0, 0, 5, 1, 0, 0, 0, 1. And then F inverse was 1, 0, 0, 0, 1, 0, 0, 4, 1. Now, because the order was swapped, this is where it gets really interesting. that when I now go through and I do my multiplication, again, notice how this is going to keep row 1 the same because it's the identity row. So 1, 0, 0, 1, 0, 0, or here, here. So 1, 0, 0. When I do my multiplication here, because I'm doing it like this, notice how this 5 is going to align with this 0 when it gets to the 4 column. This 0 aligns with that 4. So when I'm doing my multiplication, the 5 stays, which is fascinating. But when I get to my next entry, that stays a 1. And then when I get to the next entry, 5, 1, 0 times here, I still get 0. In other words, I'm keeping that inverse, the actual operation that's occurring, that multiple that I'm subtracting from here. But when I get to the next entry, notice because I'm doing here times here, it's zeros. There is no extra value of 20. Now when I multiply here, there's that multiplier that we had, and then here. So when I'm doing the inverses and I'm doing this opposite order and trying to figure out, well, what's the ultimate elimination matrix that gets created here, and I'll just call this kind of E star, we can actually use the words and what we're multiplying by to fill that in terms of its appropriate location. It's why we use that Lij notation from earlier, because now I'm going to have a lower triangular matrix where if I'm trying to eliminate that 2, 1 spot, that multiplier that I'm then always subtracting from, the positive of that is what goes in that entry. In this matrix, it's always what we're ultimately multiplying with when I get over here to this U. In other words, notice how it's lower triangular. Like ultimately when I get A by itself when we're doing this elimination process, I get A is equal to some lower triangular matrix times some upper triangular matrix, which is really fascinating. And that's going to be kind of our conclusion. I'm going to show you this with a different example. The text gets in and kind of starts showing with variables, and I'm going to leave that because I think it's pretty self-explanatory in seeing how everything kind of works together. How you find E, much like what we did here, and multiplying through generic operations. I want to show you through actually doing a problem where we have a matrix for A. We want to walk through and do the elimination and then see how when I do the inverses and I move this to the other side to get A by itself, it turns out that that inverse elimination matrix is what we were multiplying by from the very beginning. So it's really kind of showcasing this in a true example. And that's where we'll kind of leave off, because this fact is very, very important when it comes to elimination and how matrices are essentially interacting with one another, specifically elimination in particular. So from 2.1, and this example is not in the text written out, so this is kind of extra and it's included in my notes. If I have a matrix A, and that matrix is 2, 4, negative 2, 4, 9, negative 3, and then negative 2, negative 3, and 7. The idea is that I want to use elimination and transform this into an upper triangular matrix where I'm going to have essentially my pivots to, something, something, because we're going to use that as my first pivot. But then all of these entries are 0, and I have non-zero entries or possibly a zeros in those upper triangular spots there. And the way that we get to that is by applying elimination matrices, multiplication to this. And remember, as we go through and label, Eij is the matrix that's going to eliminate or zero out the ij position in my matrix for A. So if I look at my A, here's my first pivot point, 2. And again, we walked through this process already. I want to eliminate the 4. So what I'm going to do is I'm going to multiply. So literally just kind of think about it how we just had it. I want to multiply 2 times row 1 and then subtract from row 2. So in order to do that, that means I'm going to use my elimination matrix E21, where I'm going to have 1, 0, 0, and in the E21 spot, I'm going to put negative 2. Now, this number is going to be really important because if that's the elimination matrix, we know the inverse of it. And I'm going to actually, I think I can record it here, so I think you can see it. E21, its inverse is going to be 1, 0, 0, 2, 1, 0, 0, 0, 1, because that's what we're multiplying the first row by and then doing the subtraction. We're thinking in terms of my subtraction. Now, if I do this multiplication, and again, if I apply this to A, by multiplying on the left-hand side, so I essentially have E21 times A. Doing this multiplication, 1, 0, 0, 1, 0, 0, 1, 0, 0. The first row stays the same. Now we're going to do negative 2 times the first row, so that's going to give me 0. Negative 2 times 4 is negative 8, plus 9 is 1. Negative 2 times negative 2 is positive 4, plus negative 3 is 1. And then my third row will stay the same, because we're only affecting that second row there. So 0, 1, 1. Now the next thing I need to zero out is this negative 2 entry, so we're going to multiply by E31. So E31, we want to multiply row 1 by negative 1, and then subtract it with row 3. So that means E31 would look something like 1, 0, 0, 0, 1, 0. And then this would be 1, 0, 1. Because ultimately we want to think in terms of subtraction. You could approach this and just be like, oh, well, I'm just adding these two things together, so you can see how that's a positive 1. But the number that we're actually multiplying by is negative 1, because we're thinking about subtraction. So just something to kind of keep in mind, because that means when I come over here and I want to think about my inverse for E31, 1, 0, 0, 0, 1, 0, this is negative 1 because we're taking the opposite sign. Just kind of remember that. It's kind of tricky to kind of think about. Now, if I multiply this matrix, which is E21 times A, by this matrix, again, first and second rows are going to stay the same. Only the third row is affected by adding the entries together, ultimately. So this would create a 0 here. 4 and negative 3 makes another 0, or sorry, makes another 1. So just thinking about the second row right there. And then 7 and negative 2 would make 5. So I'm just kind of checking. And so we have E31, E21 times A gives me this matrix. Now we're really close to the upper triangular matrix form. We need to multiply by one more elimination matrix, because now that this has zeros underneath, we need to look to the next diagonal. It's not 0. We need to zero this entry out now. And so just to make some space, we have this is equal to A, we did E21, and we did E31, and then now we're going to do E32. So we want to eliminate this. So to eliminate for E32, 1, 0, 0, 0, 1, 0. Notice very similar to beforehand. Now I want to multiply row 2 by negative 1. I want to multiply row 2 by 1 and subtract it from row 3. So it's, but the language again is really kind of tricky. It always kind of messes me up. Which means what I'm actually going to use down here is negative 1 in that 3, 2 spot, because that's going to essentially take 1 and subtract it from here. So again, the elimination matrix is including that subtraction word that we're talking about, but the actual multiplier is just 1. And that's really important, because when I think about the inverse for 3, 2, like what we've been talking about, what actually goes in that 3, 2 entry is just positive 1. Because we're taking the opposite of what we've got. So now if I apply this matrix to this one, we're essentially doing row 3 minus row 2, so this will zero out here. And then 5 minus 1 will zero out, will turn into 4 when I do my subtraction. And we see that in this last row, I have 0, 0, and my last diagonal piece is another pivot point. This is my matrix for you. Now the idea, again, that we're kind of focusing on is I've applied these elimination matrices, which we could multiply together and come up with an overall matrix for E. And so we could do this multiplication. You could literally work this one times this one times this one, and we would have my overall transformation. And if you were to do that, a lot of the multiplications that we're doing would then get lost because of the way of the combinations. And you could essentially do this It's what the textbook is literally showcasing at the top of page 53 when you have just kind of the generic L, 2 1s, etc. I'm not going to walk through and do that because if I want to recover A, then I need to multiply by E inverse. I need to multiply by the inverse of these matrices, which is slowly peeling them off and multiplying in the reverse order that we did. So that means what's going to be out in front of this U is if I want to get this back down in terms of A is equal to, I'm going to have E, 2 1 inverse, E 3 1 inverse, and then E 3 2 inverse times U. This would recover the original matrix for A. So if I took this and I multiplied it by this one, then this one, then this one, notice how we're now going from bottom to top. This would recover A. But if I wanted to rewrite this as a singular matrix, which would be E inverse, just the overall inverse, if we multiply these together in that order, we don't lose these entries. And so if you go through and do this multiplication, and I showcase this in my notes, and so I'll leave it there in terms of showing it, we actually get then that this first matrix that I can multiply with U to recover A would be 1 0 0, and then 2 1 0, and then negative 1 1 1. If I multiply this with 2 4, negative 2 0 1 1, 0 0 4, we would recover the original matrix A. In other words, A is equal to this elimination matrix, the inverse of it, times the upper triangular matrix we found by doing the process of elimination. Specifically, it's called Gaussian elimination with matrices. And just to double check, in terms of the notes, I have E inverse 1 2 1 0, negative 1 1 1. If we do this multiplication, it works. You can also verify if you multiply this E inverse with the overall E, if you were to multiply these things together, it would give you I, and I kind of showed that. But the final observation here, and hopefully this kind of makes a little bit more sense using numbers, is that notice that A can essentially be broken down right now into a lower triangular matrix, because notice the 0 entries above the diagonal, and the upper triangular matrix that we're already finding for the backward substitution with the zeros underneath. So it's a very interesting observation to make that the inverse of E is L. Or another way to say it, the lower triangular matrix in this factorization comes from the inverse of the elimination matrices. And it's beautiful because we don't have to do a bunch of multiplications to uncover what L is. If we're recording what we're doing to each row in terms of that subtraction, then that's what goes in the entries. Right? We subtracted 2 times row 1 with row 2, so 2 is what goes in L in the 2 1 spot. We multiplied by negative 1 and then subtracted. We added, essentially multiplied by 1 and subtracted with the third row to eliminate the 3 2 spot. And so it's a really beautiful interaction in terms of how the factorization works. In terms of the combinations. And so in the next section, one of our big objectives is then now working through this and really building this out and trying to uncover what L and U are. And then in our final section for this chapter, notice that we didn't have to do any row exchanges. So what happens if we need to do some permutations? And then we begin to start talking about another transformation, which is transposing matrices. And so that's where we're headed next.